Welcome back to my YouTube channel. Today, we're going to tackle a crucial concept in the world of electrical engineering: sagging of transmission lines. Have you ever looked up at a power line and wondered why it does not just run in a straight line from one pole to the next? The answer lies in the fascinating phenomenon called sag. In this video, we'll explore what sag is, why it's essential, and how it affects the performance and lifespan of transmission lines. Before proceeding, if you're new here, please consider supporting the channel by liking, sharing, and subscribing to the channel. This will keep you updated on my latest videos. Stay tuned as we dive into the world of electrical engineering. Welcome back. What is actually sag? Sag in overhead power transmission lines refers to the natural downward curve that occurs between support structures, like utility poles or towers, caused by gravity. This deliberate downward curve in the transmission lines is a result of the cable's weight and tension. The purpose is to maintain a safe height above the ground and obstacles, while also allowing for the expansion and contraction of the lines due to temperature changes. Sag is meticulously calculated to ensure that the lines maintain a safe height above the ground. Let's explore factors affecting sag in transmission lines. Several factors contribute to the amount of sag in a transmission line, including 1. Line weight. The heavier the line, the more it will sag. 2. Span length. The distance between supporting structures affects the amount of sag. Longer span causes more sag. 3. Tension. The tighter the line, the less it will sag. 4. Temperature. Changes in temperature can cause the line to expand or contract, affecting sag. 5. Wind and ice. External forces like wind and ice accumulation can increase sag. Please pay attention to the following. The sag and tension of the lines change with temperature variations due to thermal expansion and contraction. Higher temperatures expand the conductor, increasing sag, while lower temperatures lead to contraction, raising tension and reducing sag. Now, let's look at effect of wind and ice on sag. The impact of ice and wind on power line conductors can be substantial and potentially harmful. Key points include: 1. Increased weight. Sag of the conductor is directly proportional to its weight. Ice accumulation on conductors adds extra weight, causing sagging and reducing vertical clearance from the ground, structures, or vegetation. 2. Increased mechanical stress. Wind forces, particularly during strong storms, exert pressure on conductors, which combined with ice increases stress on the conductors, poles, and towers. This can jeopardize the structural integrity of the power line components. 3. Sag and tension variations. The presence of ice and wind can modify the sag and tension of conductors, leading to possible conductor breakage, if the tension surpasses safe limits. 4. Power outages due to ice. Ice buildup can lead to power outages by increasing the risk of conductor failure or short circuits, and it can also damage insulators and related components. But, why is sag important in transmission line conductors? Sag is essential in transmission line conductors for several reasons. 1. Safety. It ensures that lines maintain a safe distance from the ground and nearby structures, reducing the risk of accidents and electrical hazards for both people and property. 2. Prevents overheating. Sag accommodates thermal expansion and contraction, helping to dissipate heat and prevent overheating, which could damage the conductors and cause outages. 3. Reduces tension. Allowable sag alleviates tension in the conductors, which is crucial during temperature shifts and high winds, as excessive tension can result in conductor breakage. 4. maintains electrical clearances. Proper sag maintains the necessary electrical clearances from the ground and objects, minimizing the risk of short circuits and electrical faults. 5. Resists dynamic loads. Sag enables conductors to endure dynamic loads from wind and ice without causing excessive mechanical stress. 6. Conductor lifespan. Allowing for a suitable sag in the conductor helps prevent excessive stretching, which in turn extends the conductor's lifespan by keeping it within its design limits. As we have known that the benefits of sagging, let us explore disadvantages of excess sag in power lines. Having too much or loose sag in power lines can lead to several drawbacks. 1. Decreased ground clearance. Excess sag can lower the vertical clearance between conductors and the ground or structures, heightening the risk of electrical arcing, fires, and safety hazards. 2. Loss of mechanical strength. Loose sag may impose excessive stress on conductors and their supports, increasing the likelihood of mechanical failures. 3. Conductor damage. Excess sag can cause swaying of conductors, raising the risk of contact with other conductors or objects, potentially resulting in damage, short circuits, or outages. 4. Safety risks. Loose sag presents safety hazards such as electrical shocks, fires, and other accidents. 5. Reduced efficiency. Improperly tensioned conductors can lead to increased resistance and line losses, decreasing the efficiency of the power distribution system. Now, how can we mitigating excess sag in power transmission lines? Here are some methods to mitigate excess sag. 1. Using high-temperature conductors. High-temperature conductors, such as HTLS, high-temperature low-sag, conductors, can operate at higher temperatures without excessive sag. These conductors are designed to maintain their strength and conductivity even at elevated temperatures. 2. Installing sag tension systems. Sag tension systems allow for precise control over conductor tension, enabling optimal sag management. These systems can be adjusted to compensate for changes in temperature, load, or other environmental factors. 3. Using tension clamps and suspension insulators. Tension clamps and suspension insulators can help maintain conductor tension and reduce sag. These components are designed to withstand high mechanical stresses and provide optimal support for the conductor. 4. Implementing dynamic line rating (DLR) systems. DLR systems monitor environmental conditions and adjust the line rating accordingly. This allows for more efficient use of the transmission line while minimizing the risk of excess sag. 5. Upgrading to higher strength conductors. Upgrading to higher strength conductors, such as ACSR, aluminum conductor steel reinforced, or ACSS, aluminum conductor steel supported, can provide increased tensile strength and reduced sag. 6. Optimizing tower spacing and conductor routing. Optimizing tower spacing and conductor routing can help minimize sag by reducing the distance between supports and avoiding areas with high wind or ice loads. 7. Regular maintenance and inspection. Regular maintenance and inspection can help identify potential issues before they become major problems. This includes monitoring conductor condition, checking for signs of wear or damage, and performing necessary repairs or replacements. By implementing these methods, utilities and transmission line operators can mitigate excess sag and ensure reliable, efficient power transmission. Conclusion. In conclusion, sag in transmission lines is a critical concept that plays a significant role in the design, operation, and maintenance of power transmission systems. Understanding the causes and effects of sag is essential for ensuring the reliability, efficiency, and safety of electrical power transmission. By recognizing the importance of sag and taking steps to manage it, engineers and technicians can help prevent power outages, reduce maintenance costs, and ensure the overall performance of transmission lines. That's a wrap for today's video. If you found this content helpful, please hit the like button, subscribe for more, and let me know what you think in the comments. Thanks for tuning in, and I'll see you in the next video. Take care.